Professor Gerd GIGERENZER is the longtime director at the Max Planck Institute for Human Development. He's the director of the Harding Center for Risk Literacy at the University of Potsdam and vice president of the European Research Council, of course. So yes, thank you so much for joining us as well for this month at the Institute in this program. And feel free to share your screen.
Today, I will talk about what is bias and why are we biased. And I will focus on the social sciences, in particular on those who have to do with the function of cognition, perception, and also on AI. There is something peculiar about the use of the term bias in the social sciences. First, here are three observations. First, it all started in the 1960s and 70s. The term bias was almost never used, say, in psychology before this time. And it started together with the use of the term probability theory, expected utility maximization, and this type of logical rationality, which was also absent in psychology before, say, the 1960s. And so we have now a flood of biases. There's overconfidence bias, framing, and many of my colleagues ask, what is the bias of the day? And there is also the notion of bias, that is the tendency to see systematic biases even if there's only unsystematic error or no bias in shooting distance. So how did we get to that? And this development is not just limited to the social sciences. The message that people have systematic biases, that these are stable and predictably irrational, and has led to a new form of governmental paternalism known as nudging. My second observation is that the same behavior is called a bias or the opposite rational by different researchers. For instance, according to Bayes' rule, attention to base rate is rational. But according to social scientists, prejudice is the consequence of attention to priors and base rates. And the third observation I would like to start with is the contradictory evaluation of a bias as something bad to be eliminated or something valuable that is necessary to improve, say, prediction. So black box systems like for predicting recidivism, like COMPAS, have been shown to be biased against race. Black box systems for credit scoring are suspected to be biased, but on the other hand, this negative view of the term bias squares very differently with the insight that deep neural networks profit from building systematical bias into them, and also from the insight that the mind is not a blank slate, but imposes a biased structure on the world. So in this talk, I will report about the project I'm on, and I don't pretend to have the solutions, but I'll have a number of questions and observations. So let me start with the distinction between two interpretations of bias. So bias is error. That's the first one. Biases hamper cognition and should be eliminated. That's, for instance, the message of most proponents of behavioral economics and social sciences. On the other hand, there is a different interpretation. Bias is functional. It helps us. Actually, biases are necessary for good cognition. Here are examples for bias is error. There are a number of consistency theories which postulate that deviations of judgment from logical and probabilistic rules are seen as cognitive biases, such as base rate fallacy, I mentioned, conjunction fallacy, or framing. So framing means that you should only listen to the logical structure of a message and not to its content or pragmatic use. Correspondence theories do not compare or do not define bias as a violation of consistency, but as something in the world. And so it's about deviations of judgments from states of the world. They are seen as cognitive biases, like overconfidence bias, planning fallacy. On the other hand, we have a number of approaches where bias is seen as something functional, not something to be eliminated. And here are just three examples. Biological preparedness. That means that in order to avoid, for instance, dying from learning, there are certain biases in our mind prepared. So human children, like those of our nearest relatives, have no inborn fear of snakes and spiders, but are prepared to learn this more quickly than fear of other objects, often with a single trial by observing, say, a parent who has fear of spiders. And that's enough. And you can see the logic. So the bias is built in order to protect us from suffering, from learning, from experience. A second example is unconscious inferences, where, particularly in perception, where without a bias built in, we would see nothing but chaotic sensory input. On the other hand, the bias allows us to see, but it also determines what we see. And finally, predictive power in AI and in other algorithms. We know that models that are biased, for instance, that ignore systematically part of the data, can enable better predictions. So here is the tension between these two interpretations. I give you now an illustration for how our mind uses biases in order to infer the world. And this is an example of a functional bias. On the left side, you see dots, and the dots recede into the surface. They are concave. On the right side, you see dots that pop out. I guess everyone sees that. Now, the left and the right picture are exactly the same. They're rotated 180 degrees. Why do we see them differently? Now, the situation is one of uncertainty. I will come back to that. So the problem is to infer a three-dimensional world from a two-dimensional retinal image. And this two-dimensional retinal image is compatible with many, many different worlds. And here is how the mind does it. The mind uses expectations about the world. These are the biases. They may be true or not true. First, the world is three-dimensional. Second, light comes from above. And third, there's only one source of light. These light comes from above was true in most of our mammalian history, and it's also still today mostly true. And then there's an evolved heuristic that uses these assumptions and is quite simple. If the shade is in the upper part, as here, then infer that the dots are concave. If it's in the lower part, infer that they pop out. So here we have a situation where without a bias, we wouldn't see anything. We would see a flat surface. And the bias is functional that enables us. And it also works equally with a photograph. On the left side, you see a crater. On the right side, a mountain. The picture is the same, only 180 degrees rotated. So this gives us the first interpretation that biases can actually functional and actually necessary. Here is a second example from a very different field. So Harry Markowitz got his Nobel Prize in economics for the question, how should one invest money into a number of, say, n assets? And the solution is standard probability theory. You have to estimate the returns in the future and the variance of the returns and the entire covariance matrix. I'm not going into the math here. The point is, this model assumes that the world is stable and certain in order to estimate all these parameters with little noise. When Harry Markowitz made his own investments for his own money after the time of retirement, he used his Nobel Prize winning optimization method. So we might think, no, he did not. He used a very simple heuristic that's called 1/n. It means allocate your money equally to each of the n funds. Now, this heuristic has several biases. So first, it ignores all data. The optimization model needs as many data as possible in order to estimate its parameters. 1/n is a 0 data point heuristic. It ignores all of them. It just makes the weights for the assets equal. The interesting thing is that, for instance, in the study by De Miguel, Galapio, and Uppal, they tested the mean variance model against the 1/n on seven real-world investments, and in 6 of the 7 times, 1/n made more money. Here we have a situation where a highly biased heuristic that ignores all the information can make more returns in terms of Sharpe ratio analysis criteria than an optimization model. As a side remark, Harry Markowitz would have never gotten the Nobel Prize in economics for the heuristic he used himself. Now we have an optimization bias, a bias against biases in many fields. So how can we understand that result that we just have? And I provide here one example for a statistical theory that explains us that reducing bias to 0 is not necessarily the best thing to do the moment you have some kind of uncertainty in the situation. The traditional view about, as in the heuristics and biases program, is that the total error is a function of bias and noise. Noise is the irreducible part of everything. The important insight is that the moment you do have uncertainty, you have to estimate all these parameters, like in the case of Markowitz, and you incur a new kind of error that's called variance. And I illustrate this here with two players. On the left side, there is a target, and each of these crosses is a dart. You can see that the player A on the left side has a bias, and he or she is throwing too far to the right and down. But the player has a low variance. That means all the darts are close together. On the right side, there's another player who has no bias. On average, all the darts are in the bull's eye, but only on average. That's the definition of bias. And that person has a high variance. And you can see now that the person on the left side with the bias actually gets a better score than the person on the right side. The bias variance trade-off is called a trade-off because in the real situations, there is a trade-off. The moment you reduce the bias, you typically increase the error by a variance and vice versa. And that tells us that in real-world situations where we do have uncertainty, where not everything is known, like in the Markowitz case, to reduce bias to zero is most of the time the worst thing you can do. You need to find a balance between these two errors. And that means, in other words, using not prediction methods or algorithms that have tons of free parameters, because they will create variance. But simple rules that are simple enough so that there's a reasonable balance between the bias and not. For instance, Markowitz heuristic 1 over n has a bias, yes, but no error from variance because it doesn't estimate anything. And that's a way to understand situations where a bias may be functional. And I think that one could understand these various uses of the term bias and also when they are functional or not by using an old decision in decision theory by Jimmy Savage and also before by Frank Knight between small worlds, so-called situations of risk, and large worlds, a situation of uncertainty. A small world is one in which there is perfect foresight of all possible future states of the world, all the consequences and all the probabilities. Like if you visit a casino this evening, you're in a small world. Nothing new can happen. All states are a number between 0 and 36. No 37 can ever happen. In large worlds, 37s can happen. There's no perfect oversights. And in these worlds, where there's uncertainty, we need biases. And we need strategies that are simple enough that have biases to guide us, to help us to make inferences that are better than using all the information and pretending that we live in a small world. And I wrote here, by the way, the term rationality, so consistency axioms, expected utility maximization, Bayesian probability updating, is all defined for small worlds only. And that gives us an understanding why in situations in large worlds, which are the typical situations we have to do with, these techniques by themselves are of little help. We need more than optimization. We need good biases. So let me finish. Here is my account at this point of the time, why we are biased. If you would just think that biases are something detrimental, that there's really no explanation why we have biases. And in a small world of risk, biases are actually dysfunctional. But under uncertainty, that's not the case. And our minds evolved to deal with uncertainty, not with calculable risk. And here, under uncertainty, biases are necessary to infer, for instance, the third dimension, or to improve predictions as in the bias variance trade-off. And finally, another reason why we are biased is the bias of many researchers who lack the distinction between risk and uncertainty. And that's particularly a problem in the behavioral economics, in the economics itself, and also in many other fields, where one assumes that every problem can be reduced to one of risk, to a small world, and in this way ignores uncertainty. And one doesn't realize that the so-called errors in a large world, such as framing and overconfidence bias, are actually reasonable errors and lead to reasonable behavior, and these biases can be functional. Let me stop here and thank you for your attention.
Thank you very much. Wonderful. I see Sadi has a question.
Sorry, thank you very much, Gerd. I mean, my understanding is that there is the bias that you have is useful if it's connected with some information structure that exists in the world, right? So actually, the world is not random. The world has a structure. And if we know something of the structure by past experience and we introduce this in our bias, that is more efficient. Is that, and this could be valid whether it's a small world or a big world, or?
In the small world, everyone knows the structure.
Oh, yeah, okay.
In the big world, it's uncertainty. You're right. So the one example of the inferring the third dimension, yeah, so what's out there, that is based on the three assumptions I gave, but the assumptions need not to be true. They are functional to get something done. We do not know whether the world is three-dimensional. It could be 11-dimensional, as in some science fiction film. We do not know that. So my approach is much more pragmatic. So what does the mind do to get something done, rather than to find the truth? Under uncertainty, the bullseye is typically not known.
Okay, but in the real life, in a way, we action is a repeated game, right? And so maybe we learn whether our biases work or not, and then we make strategies out of this, which is not necessarily what economists would typically think of in terms of maximization. In reality, we have several attempts, right?
Yeah. In large worlds, so except from the casino, there is no best solution that we can know. There is no optimization. Optimization is a fiction. It's used all the time. I think it's a very interesting bias that we have. We feel obliged to talk about optimization in situations where it has no meaning. And that's another interesting topic where this term comes from and how it took over. and from a situation where it has a meaning, like in a small world of risk, to all the others where it has no meaning.
Thank you.
Great. Willy, next.
Thank you very much for all these intuitions that give the impression that we do understand very complex things, actually. So two questions. The first one is that there is a growing trend of using Bayesian models or other type of models. And my understanding of Bayesian models could have something to do with what you just said. How would you relate Bayesian models to the understanding of bias and variance? And the second question is more with when we use random samples, we have also the illusion that by using random samples, we may eliminate statistical bias. And I think now that clearly gets more complicated. So what would be your input on that?
Yeah. First, on the Bayesian models. That's a very good question. So let us define them. When we talk about Bayesian models, we talk about Bayes' rule and its applications to various problems. And Bayes' rule is defined on a small world. So what Bayesian can do is to transform a prior probability distribution to a posterior probability distribution. That means if you're a Bayesian, and only a Bayesian, you can never learn anything new because you need to have all the options already to have a probability distribution that adds up to 1. So I'm aware about the hype of Bayesian models in neuroscience and in other fields, but I'm also aware that the problems that are being studied, say in fMRI, the Bayesian type of analysis, are all small world problems where it works. And the problem is whether you can generalize what the mind is doing with small world problems, which most people have never encountered in their life. And when you make generalizations about the real world, that's only hope. The Bayesian models need to be tested out of sample. They're not always tested out of sample. Bayesian is a method that has many, many free parameters. You can fit almost everything. And if you're a smart Bayesian, you can explain every phenomenon with some Bayes version. Yeah? So they need to be tested, they need to be fixed. And the bias variance dilemma tells you that you need at least test it out of sample. That means you test the parameters, you fix the parameters or estimate them of your Bayesian model of one half of your sample and test it on another one. Do this. Yeah? That's not always done. And if you do it, you will find that simple heuristics often predict better than Bayes. Just like in Markowitz's case.
That's very enlightening. Very enlightening. What is then the operational distinction between small and unsmall or big worlds? When do we leave the small world? And how does uncertainty play into this?
Well,
not uncertainty, sorry, the randomness.
Yeah. So I use the definition of Jimmy Savage. A small world is one where you know all the possible states of the world, all the consequences. And a world of risk is a specific version of a small world where you also know all the probabilities. You have no estimation problem in that world. Example, lotteries. Example, playing roulette.
Right. Thank you. And next we have Matti.
Hello, and first of all, apologies. I don't seem to be able to switch on my video, but that's less bias for your eyes. Maybe that's good. Thank you for this great talk. I have a couple of small questions. You mentioned about the kind of negative uses of negative connotations of bias, which I think is something that we clearly see, for example, when talking about AI, machine learning, and so forth. Perhaps coming back to the previous presentation, have you thought about when did this kind of negativeness enter the discourse? So where does this kind of negative understanding of use of bias come from? Is it something from the AI era, or could you say something about this? And then the second question is that as we are using a lot the term bias, I've sometimes been wondering that should there be other terms used here, and I wanted to hear your thoughts a bit. So should we start specializing, perhaps choosing other terms to perhaps clarify what kind of bias we are using in which situation? Terms like assumption, prior, inclination, and so forth. Thank you.
Let me start with your last question. Yes, it would be good to replace the term bias, which has typically a negative connotation in the social sciences, not in AI necessarily, to replace it by either enabler or intelligence heuristics, adaptive heuristics. They're all biased, and that's why they can work. On the first one question, where does this interest in negative biases, the negative version of biases come from? In psychology, I can answer it. As I mentioned before, the term bias emerged together with the interest of psychologists in Bayesian decision-making and also in probability theory in general as a model of the mind and logical and also logic. And quite a number of psychologists forgot basically everything about psychology and were turning to content-blind models like probability theory, expected utility maximization, Bayesian updating, and then tested people on this type of problems, but not on random devices as what Edwards did before. And people in Piaget, people did quite well, but filled in content like this. Kahneman, if you read Kahneman, Thinking Fast and Slow, he has all these problems. Yeah? On the assumption that people, if they want to be rational, have to neglect the entire content, everything they know about this, and not use their intelligence, but just apply one of these rules. And at this time, when this kind of logical rationality got hold, the term bias emerged by those who wanted to show that people are not rational, but at the same time were believers into logic and probability theory as the only and universal norm of rationality.
Thank you.
Great. And Uli next.
Thank you for the great talk. I have so if I understood correctly, one of your points was that biases, cognitive biases, are useful and evolved because we live in an uncertain world. I'm just wondering there whether maybe in sort of the environment we evolved to, there was more uncertainty than in the current world that we live in, because like we have reliable weather forecasts and we know that there will be food at the supermarket. So whether it would still be conceivable that our biases are in some sense too strong for the modern world and should be toned down.
Yeah. Don't trust the weather report. But more seriously, what I mean is the following. The different from a lottery and from a roulette game, the world in which we evolved and the world in which we live has uncertainty. For instance, even language is ambiguous. They're the same terms for different meanings, and vice versa. And just to illustrate with one example, the difference. So there is a well-known problem that's called a well-known bias. It's called framing bias. So if you read the book by Thaler and Sunstein on nudge, you will find the problem. So you have a severe condition with your heart. You think about a possible operation, but the operation is dangerous. So you ask your doctor, what's my prospect? Then the doctor may say you have a 90% chance to survive, or the doctor may say you have a 10% chance to die. According to the behavioral economists, you should not listen to what your doctor says, because there's no uncertainty. It's the same. 90% survive and 10% die. But intelligent people listen. They know that when the doctor says you have a 90% chance to survive, it's a recommendation to do it. Or when it says you have a 10% chance to die, it's a warning. In particular, if you live in the US, where doctors fear being sued, they count on the patient to understand. According to the logical view of rationality, this is a bias, a framing bias. According to my view, that's a sign of human intelligence. And there are experiments to show exactly doctors choose, knowingly this kind of framing. It's just one example. You wouldn't understand language if you would think logically.
Yeah, I mean, I was more wondering about, in general, whether that's a logical conceivability that we evolved biases that would hamper us in the modern worlds, nevertheless.
Uli, most of these biases, like framing bias, are no biases at all. They only look to you as biases in a small world where everything is only logic. And many of these biases are, for instance, overconfidence. If we wouldn't be overly confident, or some of us wouldn't be overly confident, there would be no startups because most fail. We might not even have discovered, we, the Europeans, might not even have discovered America if we would be risk averse and not overly confident.
Wonderful. Yes, Barry, last question.
Wonderful. Absolutely wonderful present. Thank you so much. And my apologies for being late, but I'm glad I was able to come for this and to listen to you. A very, very simple question. Do you worry about behavioral scientists?
Yes. Lots. I worry in many respects. For instance, okay, now you hit on something. Huh?
Yeah.
Many don't read.
Yeah.
So even this basic distinction between risk and uncertainty are not known to many. They're so important because under risk you can optimize, under uncertainty you can't. There is lots of fashion. For instance, when I mentioned Thaler and Sunstein, they called their theory before, or their approach before, anti-paternalism, and few listened. Then it was called some libertarian paternalism, very few listened. Then they called it nudge, and now it's a great thing. Just to illustrate. And that's what I worry. And I also worry about the methodological training. We have more and more studies that are no longer experimental studies, that are no longer controlled. One just spends, so Amazon Turk type of studies which have very little control. So there's a number of things I worry about. But probably everyone in other fields also has this another type of worries.
Yeah. You and me both. Thank you. Yes. Yeah. That's one. Thank you so much.
Wonderful. Thank you so much. This is all the time we have for this section. Thank you so much, Professor Gigerenzer, for your talk, and everyone for your comments and questions.